lighting is the okay. The 42nd lecture, frequency domain analysis of LTI systems excited by random inputs. We had discussed the statistical properties of the output of an LTI system. Xt is a random input and Yt is the output. Yt is also random. We showed how to find out y bar and y squared bar and also Ry tau. Ry tau was expressed, all these quantities were expressed in terms of x bar squared, no, x squared bar and Rx tau. The next probability, the next statistical description is the cross correlation between y and x, and the cross correlation is defined like this: R xy tau is equal to expected value of xt and yt plus tau. I will do one of the derivations, the other you can do yourself. This obviously is expected value of xt and yt plus tau is minus infinity to infinity, minus infinity to infinity x t plus tau minus lambda, a convolution with h lambda d lambda. And what you do is, again you interchange the integration and expectation. So you get minus infinity to infinity, expectation of xt and xt plus tau minus lambda would be simply Rx of, yes, or lambda minus tau. Does it make a difference? Alright, let us take it tau minus lambda. Oh no, Rx of tau minus lambda. It does not make a difference. Then multiplied by h lambda d lambda, and you can see interestingly that this is simply Rx of tau convolved with h of tau. Is that clear? R, the cross correlation coefficient, is simply the convolution of Rx tau and h tau. Now if I take the other cross correlation, that is Ryx of tau, what do you think the change shall be? Pardon me? Ryx tau, what do you think shall it be? It will be minus infinity to infinity. Then instead of tau minus lambda, I shall have tau. No, isn't that clear? We should have Rx of tau plus lambda, h lambda d lambda. That is all the change there shall be, because what we have to do is to take the expected value of xt plus tau and then yt, expected value of this. So this would be, in the integral, this would be xt minus lambda, and if you take the difference between the two arguments to find out Rx, it would be tau plus lambda. Is that clear? Now is this point clear, or do I have to do the algebra? I think this should be clear. Yt shall involve integral of this, then h lambda d lambda. You combine this and this, take the expectation, then you get Rx of tau plus lambda. Now can this be viewed as a convolution? Can this be viewed as a convolution? No, it is not a convolution of Rx tau with h tau. However, it indeed can be viewed as a convolution if you change lambda to minus lambda, put lambda equal to minus lambda prime, change the variables, then yes, you can. It would be a convolution with, instead of h lambda, h of minus lambda. But we will leave it as it is. We will not, h of minus lambda, we will not bring that into the picture. We will say Ryx of tau is this, and you notice, well, let me also write Rxy tau. This is minus infinity to infinity, Rx tau minus lambda, h lambda, d lambda. And you notice that Rxy tau is not necessarily equal to r x y tau. These two are not necessarily equal, but you also notice that if you put tau equal to 0, they are absolutely identical, and therefore r y x 0 is equal to r x y 0. What is the physical interpretation of this? The cross correlation coefficient at tau equal to 0. It has no particular physical significance. The only thing is it obeys the inequality that r x y tau mod is less than equal to square root of r x 0 and r y 0. Is it okay, Abhay? Or you don't remember? You do remember. That's wonderful. Okay. Suppose Rx tau, suppose it's the input is a white noise process. That is, Rx tau is S0 times delta tau. Well, then what would be Rxy tau? This is Rx tau convolved with H tau, and therefore this would be simply equal to, yes, what would be the value? If Rx tau is this, the value would be S0 times H tau. On the other hand, Ryx tau, which is minus infinity to infinity, Rx tau plus lambda, H lambda d lambda. We check the temptation of equating this to a convolution. We will keep it as it is. Now, if this is S0 H tau plus lambda, I beg your pardon, S0 Rx tau plus lambda is delta tau plus lambda, alright. Then what would be the value of the integral? It would be S0 H of minus tau. Now, you notice why they are not equal. Rxy tau is S0 H tau and Ryx tau is S0 H of minus tau. If the impulse response is an even function, then they should be equal. Not in general though, it is a particular case for white noise process, alright. Let's take an, I think I'll skip the example. We consider then analysis in the frequency domain. In the frequency domain, the quantity that we have been familiar with is the spectral density, that is Sx of omega, and Sx of omega is simply the Fourier transform of Rx of tau. This we have established already, alright. So, if we know Sx of omega, the spectral density of the input random process, is it possible to find out Sy of omega? This is what we are asking now. And if I want to find Sy of omega, obviously the thing to find would be Ry of tau, that is the autocorrelation of the output process, and we have already derived an expression for this. Ry of tau, you recall, is equal to minus infinity to infinity, and I said unfortunately this cannot be simplified further. So, let us write the complete expression, d lambda 1, then minus infinity to infinity, Rx of lambda 2 minus lambda 1 minus tau multiplied by H lambda 1, H lambda 2, d lambda 2. This is the expression. Now, if I take the Fourier transform of this, let me use a different color. If I use the Fourier transform of this, what does it mean? It means that I use another integral from minus infinity to infinity, and I multiply by e to the minus j omega, yes, tau d tau, alright. This would be equal to Sy of omega. Now, let us see how we carry out this integration. What we do is we first integrate with respect to tau, and therefore what we will get is minus infinity to infinity d lambda 1 minus infinity to infinity H lambda 1 H lambda 2, they do not involve tau. Then the third integral is minus infinity to infinity Rx lambda 2 minus lambda 1 minus tau e to the minus j omega tau d tau. Is that okay? There is something I am missing. What? D lambda 2, let us put it here, d lambda 2. Now look at this carefully. I would omit a couple of steps. I would go to the simplification right away. Notice that that this function, the argument of this can be negated without any change, all right. So I can write this as lambda minus, I am sorry, tau I can write this as tau minus what? Lambda 2 minus lambda 1. Is that okay? If I negate the argument of this, I can write this as Rx tau minus lambda 2 minus lambda 1. Now if lambda 2 minus lambda 1 was not there, if it was not there, then what we get is simply Rx tau e to the minus j omega tau d tau. What does it imply? It is simply Sx of omega. Now instead of Rx of tau, I have Rx of tau minus a constant. The Fourier transform of f of t minus a is simply e to the minus j omega a multiplied by the Fourier transform, and therefore the result for this is obvious. I therefore write Sy of omega as equal to minus infinity to infinity. This derivation is an extremely elegant derivation. Minus infinity to infinity h lambda 1 h lambda 2 d lambda 2, then I have Sx of omega multiplied by e to the power minus j omega times lambda 2 minus lambda 1. Is that okay? The Fourier transform. Now Sx of omega is simply a constant as far as this integration is concerned, because the integration variables are lambda 1 and lambda 2. Therefore I can bring this down here, Sx of omega. Then lambda 1 and lambda 2 are independent of each other, and therefore I can separate the two integrals. Let us first do with respect to lambda 1, h lambda 1, the only other term in lambda 1 is minus j omega minus lambda 1. So e to the power plus j omega lambda 1 d lambda 1 and multiplied by minus infinity to infinity h lambda 2 e to the minus j omega lambda 2 d lambda 2. Is that okay? I have separated the two integrals because lambda 1 and lambda 2 are independent of each other. And if you notice carefully, what is this? Isn't this simply equal to h of omega? That is the Fourier transform of h lambda. Lambda 2 is a dummy variable, all right. And what is this? H of minus omega. And we know that this is a complex conjugate of the other. And therefore, the result that we establish is Sy of omega equal to Sx of omega multiplied by h omega and h of minus omega, which means that it is h omega whole squared. This is exactly like the system function, except that it relates the spectral density, that is the power of the output, to the power of the input, and therefore this quantity h of omega magnitude squared, which is Sy omega over Sx of omega, is called the power transfer function. In the frequency domain, you see the analysis is very much simplified, because it's simply a multiplication of the input spectral density by the power transfer function, and power transfer function is very simply related to the voltage transfer function or current transfer function. It's simply the magnitude squared, all right, and this affords a lot of simplification in actual practice. Well, let's write it down again. Sy omega equal to Sx omega multiplied by h of omega multiplied by h of minus omega, h of minus omega. If I transfer this to the S plane by analytic continuation, then I shall write Sy of S. I simply replace omega by S by j. and I change the functional notation as x of s, what shall I get here? H of s by j. Shall we change this to h of s? Well, I write this as h of s is equal to h of s by j. Do you understand why I am changing the notation? Because the functional form is different. I cannot write this by analytic continuation capital H of s. No, I cannot write that because the functional form is different. So, h of minus s, alright. This is in the s domain by analytic continuation, and as you know, in evaluation of integrals, it is this form which is preferred because you can then evaluate by contour integration or by tables as the case may be. I told you that tables for n polynomial, I am sorry, a rational function of degree n equal to 1 to 10, these are available for calculation of the mean squared values, x squared bar or y squared bar. What I mean, let me illustrate with an example. Suppose we have a simple RC network. This is our favorite network because it illustrates many concepts. You know that h of s is equal to b by s plus b, alright, and therefore if Sx of omega is given, then Sy of s shall be equal to Sx of s multiplied by h of s times h of minus s, which is b by s plus b multiplied by b by minus s plus b, alright. So, this is equal to Sx of s b squared divided by b squared minus s squared, okay. Suppose the input process is white noise, that is Sx of omega is equal to s naught, then what is Sx of s? It is the same. So, this would be equal to b squared s naught divided by, let us write this, s plus b times minus s plus b. Now, if I want to find out the mean squared value, what do I do? Y squared bar, I write this as 1 over 2 pi j, if you recall this integration, minus j infinity to plus j infinity, and then s y of s, then ds. And as you recall, hopefully, that if we write this as n of s, n of minus s divided by d of s, d of minus s, ds, and we choose n of s and d of s to contain the left half plane roots, in this particular case, what would be n of s? No, it would be b square root of s, because n of s, n of minus s is b squared s naught, and therefore one part, it is a constant, square root of this is to be given to n of s, square root of this is to be given to n of minus s. And obviously, this is equal to, in terms of polynomial notation, c 0, all other constants are 0. D of s is equal to s plus b, and s, therefore c, I am sorry, d1 is equal to 1 and d0 equal to b, and this integral shall then be evaluated as, it is a first order polynomial, first order rational function, therefore n equal to 1, and the integral shall be evaluated as I1, which is tabulated in the book. So, we take account of that integral, that expression, and we can evaluate y squared bar in this case as, you can do the algebra, the final result is b s naught divided by 2. This is the result. Do you know, do you recall how this formula was obtained? What is the genesis of this formula?
Sir, our autocorrelation factor equal to 0.
That's right. An autocorrelation function was the inverse Fourier of the spectral density. It is an inverse Fourier transform, and then it put tau equal to 0. All right. We take a next example, the same network RC, but the input process is not white, it is colored noise. And suppose Sx of omega, you recall that a low pass kind of noise would have a spectral density like this. And we took an expression earlier which is beta squared S naught divided by omega squared plus beta squared, or beta squared plus omega squared. All right. What is the autocorrelation function of this? What is the inverse transform of this?
S naught e to the power minus beta
S naught e to the power minus beta mod tau. I think there should be a beta and the division by 2. I am not sure. This is the autocorrelation function, and this is an autocorrelation function of colored noise. Colored noise because the spectral density decreases with frequency. Okay. If this is so, and we are interested in finding Sy of omega from which we find y squared bar, then carrying out the algebra, we see that Sy of S would be equal to b squared beta squared S0 divided by S squared minus b squared multiplied by S squared minus beta squared. Is that difficult to see? Sx of omega, I convert this to Sx of S, and what I get is minus beta squared S naught divided by S squared minus beta squared. Actually it is minus S squared plus beta squared, I take a negative sign, and then I multiply by h of S times h of minus S, which is b squared divided by b squared minus S squared. Is it okay? No, minus S plus b, yeah, okay. And then this is what I obtain, Syx. Now if I integrate this, that is if I take y squared bar as 1 by 2 pi j minus j infinity to plus j infinity b squared beta squared S naught divided by, let us write this clearly, S plus b S plus beta, then I have S minus b S minus beta. Can you tell me, multiplied by ds, can you tell me what is n of S? B beta square root of S naught. All right, and d of S? S squared plus b plus beta S plus b beta. Now you have to be careful here, because if this is n of S, then n of minus S is not in this form. N of minus S should have been, d of minus S should have been minus S plus b times minus S plus beta, and because both have negative signs, the product can be retained in this form. If it was not so, then your n of S had to be changed, the negative sign had to come somewhere. Alright, is that clear? Now what is this integral now? This integral is obviously I2, and you have C0 equal to this, D0 is B beta, D1 is B plus beta, and D2 is equal to 1. Now you substitute in the formulas and evaluate I2. The final result is y squared bar is equal to B beta S naught divided by twice B plus beta. And you see that if beta is much greater than B, if beta is much greater than B, then what is the input noise process? It approximates white noise. Then y squared bar tends to, if beta is much greater than B, then it tends to B S naught divided by 2, which is also white noise. Is that clear? Which is also white noise. Yes or no?
Output of white noise.
Y squared bar has nothing to do with white noise.
Output of white
Output of,
noise.
what do you mean output of, yeah, okay. Mean squared value of the output of white noise. Alright. The point that I want to mention is that if the bandwidth of the input process, which is determined by beta, is much greater than the system bandwidth, then the system behaves as if it is fed with white noise. That is the only point that I wanted to mention. We finally define the cross-spectral density. It is not a matter of definition, it is a matter of derivation. You know that R x y tau is the convolution of R x tau with H tau, and R y x tau, we did not want to confuse it with convolution, we simply wrote R x of tau plus lambda H lambda d lambda. There is something we can do though. I can write it in terms of Rxy, can't I? Can I or can I not? Minus tau, that is right. If I write this as minus tau, then it becomes lambda minus tau, and lambda minus tau obviously can be written as tau minus lambda also, and then it becomes a convolution. Agreed? Now, with this we can therefore find out by applying the definition what are the cross spectral densities S x y of omega. What shall this be? Obviously it would be the product of, you see, R x tau convolved with H tau. So if I take the Fourier transform, obviously it will be product of Fourier transform, that is, it would be S x of omega multiplied by H of omega. And similarly, S y x of omega shall be equal to, now this is R x of R x y minus tau. What about the Fourier transform of this? It would be simply omega shall be replaced by minus omega. So, S x of minus omega, H of minus omega. But what is S x of minus omega? The spectral density has to be positive, even and real, and since it is an even function, therefore this is simply S x of omega, H of minus omega. These are very interesting relationships. These are reflections of the relationships in the time domain. Now, in the time domain also similar relationships hold. I shall conclude this class by working out an example from the textbook 1211. Very practical example, and I could not check the temptation of working this out. This is one of my favorite examples. It says that a random process has sample functions of the form xt. The random process has sample functions of the form xt equal to x naught plus nt, where x naught is a DC, a constant, and nt is random noise. A simple process, that is, random noise is mixed with a constant DC level, random noise whose autocorrelation function Rn tau is, it is a colored random noise, and therefore it is of the form some constant multiplied by e to the minus another constant mod tau. Well, for simplicity it is simply given as e to the minus tau. This is what is given. It is desired to estimate x0. Well, when it is transmitted from one place to another, the constant, well, it becomes mixed with noise, and therefore you do not know what the value of the constant. So, at the receiving end you want to estimate what the value of x naught is. It is desired to estimate x naught by passing xt through a single section RC filter. This is fed here, and it is required to estimate from the output the value of x naught, alright. If the noise at the output of the filter, that is the output due to NT, it is a linear time invariant system, therefore the outputs are can be isolated from one another. If the noise at the output of the filter is to have an RMS value of 1% of x naught, the noise at the output of the filter, if the noise output of the filter is yn, then what does this represent? The RMS value. What do you mean by the RMS value? It is the square root of yn squared, mean, alright. This is to be 1% of x0, and x0 has a true value of 0.1 volt. Why did you say true value? Because you are estimating. The true value, the actual value is 0.1 volt, alright. So we have to design this filter in such a manner that the output noise is only 1% of x0. Well, if it is only 1% of x0, obviously the output shall basically and principally be x0. We can forget about the noise part. Now what should be B? That is the process. Let's understand this physically. NT is colored noise, alright, and you want to filter out the noise, you want to estimate x0, okay. So you well, colored noise has a spectrum, and if you can get rid of the spectrum, obviously it's very nice, but the colored noise also has a DC value. If it did not have a DC value, for example, if this was a band pass noise, then we could get x0 exactly by passing through a band pass filter. This is a low pass filter. So through a low pass filter, all that you can do is to reduce the noise root mean squared value, RMS value, as compared to what shall be the output. Now if no NT was there, what would have been the output? Simply x0, alright. So what is basically, then we have to find out what is B, alright. The problem is tackled like this. Your y of t output is h of t star x of t, and therefore it is h of t star is for convolution, x naught plus h of t star nt. Now what is this? ht is of course b e to the minus bt ut, because it is a simple RC filter. But what is this then? Pardon me? X naught times this. No, this is a convolution.
So it's x naught times integral of ht dt from minus infinity to plus infinity.
What is this?
H of 0.
What is h of 0?
Capital H.
What is the numerical value? Look at the figure and tell me. 1, and therefore it is simply x naught. It does not require any integral evaluation. A DC passes undiminished through an RC low pass filter. Therefore this is, and let us call this as y2. Therefore my output is equal to x naught plus y2, and it is y2 squared mean that we have to find out, and we have to reduce it to a particular fraction of x0. Let us see what is y2 squared bar. That is the noise output. If you recall, we have to go back to the formula, minus infinity to infinity d lambda 1 minus infinity to infinity h lambda 2 h lambda 1 Rx of lambda 2 minus lambda 1 d lambda 1 d lambda 2. Is this formula familiar? We had written Rx of tau, Ry of tau in terms of this, and there was an additional term lambda 2 minus lambda 1 minus tau. That tau is missing here because we are evaluating the mean squared value, which is R, which is the autocorrelation at tau equal to 0. Now if you substitute this, if you substitute here Rx of lambda 2 minus lambda 1 is equal to e to the power minus lambda 2 minus lambda 1 e to the minus mod tau, alright, and you substitute h lambda is equal to b e to the minus b lambda, then the evaluation of this integral shall require a little bit of care. Why? What is the reason? You cannot do it blindly because b e to the minus b lambda times u lambda, thank you, and therefore the integral shall be from 0 to infinity, alright. The lower limit shall be 0, but it is not that care which I am asking you to exercise. I am asking you to exercise care because of this mod, and therefore when you say well, let us write down the integral. It would be b squared 0 to infinity e to the minus b lambda 1 e to the minus b lambda 2 e to the minus lambda 2 minus lambda 1 mod d lambda 1 d lambda 2. Alright, this can be written as b squared integral 0 to infinity e to the minus b lambda 1 d lambda 1, then the rest of the integral is e to the minus b lambda 2. Now you have to separate this into two integrals. One is lambda 2 less than lambda 1, the other is lambda 2 greater than lambda 1. Alright, the first integral, for example, would go from 0 to lambda 1, and the second one would go from lambda 1 to infinity, and we shall have e to the minus b lambda 2. Then what should be here? E to the minus lambda 2 lies between 0 and lambda 1, and therefore e to the minus lambda 1 minus lambda 2. Is that okay? Lambda 2 is less than lambda 1, and therefore, and the power of e must be negative, and therefore this is the result. This multiplied by d lambda 2 plus integral lambda 1 to infinity. This is the point of the whole problem. This is where people falter. And the other is the same thing, e to the minus b lambda 2. Now you shall have e to the lambda 1 minus lambda 2 d lambda 2. If you evaluate this, the evaluation is a little messy, but nothing difficult. It's after all integration of an exponential. It's a definite integral. If you carry out the algebra, the final result that I get, which I am not 100% confident, but this is what I get. Y2 squared bar is this. b by 1 plus b, and what we have to estimate is y2 square bar square root. This is the RMS value, and this RMS value is therefore b by 1 plus b, and this has to be 1%, that is 0.01 of x0, and x0 is 0.1 volt, and therefore this is 10 to the power minus 3. Therefore b by 1 plus b is 10 to the minus 6. So what is b? Yeah. Put an approximation sign, although it's more or less exact. And it is at this point that I wish to conclude this class. Thank you so much. I enjoyed teaching you.